Let's study chapter 15, problems 6 and 8. So problem 6 is on page 409. And it deals with the problem of angular momentum. Now, angular momentum is a conserved quantity. It's momentum that is going around in a circular direction, and it's conserved. And the angular momentum is a product of the mass times the velocity at the radius, equatorial radius, times the radius itself. So the classical figure is of a figure skater that spins around at a certain speed, and without changing their energy, they just draw their arms in, giving themselves a smaller radius, and their spin rate picks up, because the product of V times R is a constant. So let's examine motion in a circle. If an object is going around a circle at a velocity v, then the distance that it goes around the circle is the circumference. That's equal to 2 pi r, as you know from geometry. And the amount of time that it takes to do is 1 period to go around, which we'll call by the letter t. So the amount of time that it takes to go around the circle is t, 1 period. The distance that it goes is 2 pi r. Now, velocity is always distance over time. So the velocity of an object on the equator of a revolving sphere is going to be 2 pi r over t. So if we substitute this into the original angular momentum equation, that angular momentum equals mvr, and now we have that v is equal to 2 pi r over t. We have this is equal to m times 2 pi r over t times another r. So it's equal to 2 pi m times r squared over t, where r is the radius of the object and t is the period that it takes to go around once. And this is a conserved quantity. So if we have two objects, one of which is larger and is given to us as a core of a supernova star, and it has a radius of 10 to the 4 kilometers, and it's going to collapse into a very small object that has a radius of 10 kilometers. And the original rotation speed, t, is given as 1/2 day, which is 1/2 times 24 times 60 times 60 seconds. So that is equal to 1/2 times 24, which is 12. So it's equal to 12 times 3600. And that comes out to be 43,200 seconds. So the core of the supernova, just before it collapses, has a speed at the equator of it of 43,200 seconds, not a speed, but a period, the amount of time it goes to go around. And now this has a radius. This is called step 2. R2 is equal to 10, and we want to know is what T2 is equal to. What's the new period when R1 is equal to 10 to the 4th? Now we have the conservation of angular momentum, as we saw on the previous board, that the conserved quantity is 2 pi m r squared over t. Is always conserved, so it's conserved before and after as well. And so that means that before and after. So before we have 2 pi m r1 squared over t, and after we have 2 pi m r2 squared over t, 2. And this is t1. So now you see that the two MRs cancel, and what we have left is that R1 squared over T1 is equal to R2 squared over T2. Now this is a fraction on one side of the equation, fraction on the other side of the equation, so we're permitted to cross multiply. So we have R1 squared times T2 is equal to T1 R2 squared. Now, if we divide both sides by R1 squared, then we have the sought for quantity. What we have is that, because we have cancellation over here, we have that T2 is equal to T1 times R2 squared over R1 squared. So now we're just going to put in the numbers. We saw a moment ago that T1 was 43,200. Now R2, the final radius, is given as 10 kilometers, so we're going to put in a 10 for that. So that's 10 squared, and on the bottom, the old radius was 10 to the fourth, so we have a 10 to the fourth quantity squared. So let's continue with the arithmetic, and we're going to have that that's equal to 43,200 times 10 squared over 10 to the 8th. Now we can rewrite this as 4.32 times 10 to the fourth times 10 squared over 10 to the 8th, and that's 4.32 times 10 to the 6th over 10 to the 8th equals 4.32 times 10 to the minus 2 is equal to 0.0432 seconds. 4/100ths of a second is the new rotation period. And they ask us to compare this with the given data for pulsars that are in chapter 15. And in chapter 15 we find that the Crab pulsar has a period of 1/30th of a second, which is 0.03 seconds. So you see, this compares very, very favorably with the data. So the second problem that we're going to do is problem number 9. And I'll read this problem. It's on page 410, number 9. It has 3 parts, A, B, and C. The problem reads, using, number 8. We did 9 earlier. So now we'll do 8. Calculate your Schwarzschild radius. How does that compare with the size of an atom? And how does it compare to the size of a proton? So A, your Schwarzschild radius. The Schwarzschild radius is equal to 2gm over c squared. It's equal to 2 times 6.67 times 10 to the minus 11th, which is g, times your mass in kilograms. And I'm going to take my mass in kilograms to be 80 kilograms. And it's divided by the speed of light squared. 3 times 10 to the 8th times 3 times 10 to the 8th. So on the top, we're going to get 2 times 6.67, which is about 14, times 80, and then times 10 to the minus 11. And on the bottom, we're going to get 9 times 10 to the 8th times 10 to the 8th. So continuing with the arithmetic, we see that 9 goes into 80 about 9 times, and 9 times 14 is about 120. And that's times 10 to the minus 11th on the bottom, at top, and 10 to the 16th on the bottom. So this is going to be a net of 120. Now 10 to the minus 11 over 10 to the 16 is equal to 10 to the minus 11 minus 16. Equals 10 to the minus 27. So it's 120 times 10 to the minus 27. Now, this is approximately equal to 10 squared times 10 to the minus 27, which means that it is about equal to 10 to the minus 27 meters. So your Schwarzschild radius is 10 to the minus 27 meters. That's 26 zeros and a 1 meters. And if your mass had shrunk down to that small, then light would not be able to escape from your surface. So let's compare this to the size of an atom. So B, you have to look up size of an atom. You have to Google this somewhere. Size of an atom equals 10 to the minus 10th meters. So U over the atom equals 10 to the minus 27 over 10 to the minus 10th. So that means that you are 10 to the minus 17 times smaller. You're 10 to the minus 17 times smaller than the atom. See, compared to the size of a proton. So again, you look up on Google the size of a proton, and the size of a proton is 10 to the minus 15th meters. So you compare U to a proton, and you are 10 to the minus 27, proton 10 to the minus 15, so you are 10 to the minus 12 times smaller than a proton.